Imagine a world where the most advanced semiconductors aren't forged in Eindhoven or Hsinchu, but in Dongguan, and where the company best known for smartphones delivers the lithography tools that define the limits of Moore's Law. That scenario, once pure science fiction, now seems within the realm of possibility. According to multiple unconfirmed but consistently reported industry whispers, Huawei and China's largest contract chipmaker, SMIC, are collaborating on a domestically engineered extreme ultraviolet lithography system. If they truly achieve even partial success, the implications for global chipmaking, technology competition, and geopolitical power balances would be profound. It's no secret that EUV represents the holy grail of high-volume, leading-edge chip production. Since the first commercial EUV tools emerged from ASML's headquarters in the Netherlands nearly a decade ago, semiconductor leaders like TSMC and Samsung have depended on these machines, each costing over $150 million to etch circuits with 13.5 nanometer wavelength light. These systems enabled the jump from multi-patterned immersion lithography at 193 nanometers down to single-exposure techniques for sub-7 nm and beyond. But ASML's near monopoly, coupled with stringent export controls, left China's chipmakers on the outside looking in. Until now, that is. At the heart of this alleged breakthrough is a technology known as laser-induced discharge plasma, or LDP. Unlike ASML's laser-produced plasma approach, which relies on immense, precisely tuned pulsed lasers striking tin droplets to create a high-energy EUV source, LDP uses electrical discharges to ionize tin vapor. In principle, LDP promises several advantages: less dependence on imported high-power lasers, simpler optical architectures, and potentially dramatically lower per-tool costs. Early laboratory setups have reportedly achieved output powers of 50 to 100 watts, still far below the roughly 250 watts required for high-throughput production. But a significant step for a system built entirely with Chinese source components. According to industry observers, Huawei's R&D team in Dongguan has been quietly testing a prototype LDP-EUV scanner since early 2024. SMIC, which just opened its N+1 pilot line in Shenzhen last November, has been evaluating these early units for patterning 7 nanometers node wafers. Using advanced photoresist supplied by Shanghai Microelectronics Equipment. Internal roadmaps, leaked to technology news sites such as XFastest and WCCF Tech, suggest trial production in the third quarter of 2025, with volume shipments of commercial LDP-EUV tools slated for late 2026. At least one veteran lithography specialist, Dr. Kim, formerly a senior researcher at TSMC and a consultant for Samsung's Xi'an fab, publicly acknowledged on social media that China's push into LDP-EUV caught him off guard, describing it as a deep tech leap few saw coming. Yet tremendous challenges remain. ASML's flagship NXC 3800C machines operate at upwards of 250 watts with uptime exceeding 95%, benchmarks only achieved after years of incremental refinements across optics, source modules, photoresist chemistry, and throughput management software. Replicating that maturity requires not only hardware innovations, but also a robust ecosystem. Precision optics from Zeiss, reliable tin droplet generation, and debris mitigation. Resist suppliers capable of delivering nanometer-scale pattern fidelity, and fab integration teams accustomed to EUV's ultra-clean vacuum environments. While China has made serious strides in each area, Shanghai is now home to one of the world's largest optical glass manufacturing clusters, and MEMC-grade semiconductor chemicals are in production across multiple plants. The integration of these subsystems into a fully functional, high-yield EUV platform is a task of Herculean proportions. Even so, China's semiconductor strategy leaves it little choice. After all, the United States tightened export restrictions in April 2025, barring any shipment of advanced lithography equipment or key components to mainland China. The U.S. Commerce Department's decision, aimed at hobbling Huawei's ambitions and curbing SMIC's ability to push below the 14 nanometers node, also had the unintended effect of accelerating Beijing's push to indigenize. With ASML off limits, Chinese policymakers have poured billions into state-backed research consortia, tax incentives for domestic equipment suppliers, and direct subsidies to chipmakers willing to adopt homegrown tools. In effect, the sanctions may have backfired by catalyzing a securitized, strategically driven semiconductor ecosystem. What, then, is the state of play today? On the dry side, major Chinese DUV immersion lithography tools, operating at 193 nanometers, still rely on multi-patterning to achieve critical dimensions below 7 nanometers. This approach requires up to 4 separate exposures per layer, driving up fab complexity, throughput bottlenecks, and yield loss. SMIC's yield rates on its current 7 nanometers nodes lag well behind TSMC's. And Samsung continues to lead in both 5 nanometers volume and 3 nanometers pilot production. Huawei's own foundry services, spun off as Skywater-style joint ventures in 2024, have only recently begun sampling chips from their 7 nanometers lines, with yield improvements of around 5 percentage points since last year. Without EUV, China's best hope for parity lay in smaller refinements, lean manufacturing upgrades, incremental materials enhancements, and collaborations with global IP vendors. But LDP-EUV promises a genuine paradigm shift. Looking ahead, several milestones bear watching. If a third-quarter 2025 pilot line produces workable wafers at 100W source power, that will validate the core concept. Scaling to 150W by early 2026 would signal real momentum, as toolmakers refine arc discharge chambers and collector optics to boost efficiency. Achieving consistent 250W outputs with stable resist sensitivity and acceptable defect densities by the end of 2026 would mark the point at which China's first generation of EUV scanners could enter volume production for 5 nanometers and 3 nanometers technologies. By 2027 and beyond, if SMIC integrates these tools into its Shenzhen fab alongside Huawei's in-house foundry facilities, China could close the gap on advanced node performance per watt, challenging NVIDIA's next Blackwell accelerators in AI inference workloads and giving local AI hardware startups a fighting chance to compete. Of course, even if Huawei and SMIC meet these timelines, capacity will be limited at first. Early Chinese EUV tools might number only a few dozen units by 2028, far short of the hundreds deployed annually by TSMC. But each incremental gain helps solidify a domestic supply chain. Optics companies, such as the Shanghai Institute of Optics, would refine their Zeiss-comparable glass. Resist manufacturers like JSR Technology China would optimize their formulations. And back-end service providers would adapt to EUV's unique handling requirements. That self-reinforcing ecosystem, once matured, could support the development of 2 nanometers or even 1.5 nanometers nodes by the early 2030s, machines that, today, rest squarely within ASML's roadmap and U.S. licensing frameworks. Beyond the fab floor, the geopolitical stakes could not be higher. China's ability to field its own EUV equipment would undermine the effectiveness of Western export controls, limit the leverage of ASML and its Dutch government backers, and recast the semiconductor landscape into a multi-pole world. American chip design firms might find themselves negotiating with both TSMC and SMIC for production capacity. Alexandria Ocasio-Cortez call for reshoring critical technology could take on new urgency in Washington. And Europe's ambition to cultivate a digital sovereignty might hinge on reviving local EUV tool suppliers or partnering with Asian innovators. Yet for now, caution is warranted. Past proclamations of ASML killer technologies have stumbled on practical realities. Gallium nitride etchers failed to match high-volume chemical vapor deposition lifetimes. Graphene interconnects couldn't scale beyond lab prototypes. And domestic photomask producers struggled with sub-10 nm reticle fidelity. Huawei itself endured years of setbacks on the Ascend AI accelerator line before shipping the Cloud Matrix 384, and SMIC's infighting over technology licensing has sometimes delayed rollouts. A small misalignment in a collector mirror, a photoresist contamination issue, or a power supply instability could negate months of progress. Even the best-funded efforts require relentless engineering discipline and a tolerance for repeated failures. Still, the very idea that Huawei, a company once known primarily for handsets, could move to the heart of chip-making optics underscores a new reality. Whether they will truly deliver a full-scale, high-yield LDP-EUV system by 2026 remains the biggest question mark in semiconductor history. If they do, the global industry will face a choice: compete with a newly empowered Chinese ecosystem, double down on innovation, and perhaps forge fresh alliances, or attempt to hold back the tide with further export curbs, risking the creation of technological bifurcation that stifles creativity on both sides. For now, the race intensifies. Keep an eye on Huawei's Dongguan campus, where a handful of LDP-EUV scanners hum in cleanroom silence, and on SMIC's Shenzhen pilot lines, where engineers probe each etched wafer for defects measured in single digits of atoms. Should those trial runs succeed, the long-standing assumption that only ASML could deliver EUV will shatter, and a new chapter in chipmaking will begin. One in which China's semiconductor ecosystem stands not as a follower, but as a peer, challenging the West on its own terms.